Hi, in this Linux video, we're going to look at hard links and symbolic links. We will see how we can distinguish between them, how we identify different files and different links, what a link is. We'll look at hard links and see what the major characteristics are, how we would create them, delete them, and we'll look at examples so we can understand how they function and how we create them, what we can and cannot do with hard links. We'll then look at soft links, also called symbolic links, and understand how we create them and what the main features are, what we can and cannot do with soft links. Then we'll compare the hard links and symbolic links because they're similar in many ways and different in others. And finally, I'm going to give you some practical examples so that you understand how you can use the hard links as well as symbolic links when you're working on Linux. So let's get started. Before we do that, well, the first concept I want to introduce to you is the concept of inode or the information node. So let me log into the Linux system here. So I'm in my home directory inside a subdirectory. So I'm inside a subdirectory called Praveen. If I look at what I have here, I have a whole bunch of files and some directories here. So normally we just do an ls-l command, for example, and we know that if we see a D in front of something, that's a directory. So these blue coded ones are directories, and the one that has nothing in front of it is really a file. If you make a copy of the file, what the system is doing, what the operating system is doing is it's taking the data that's inside that file and writing it again in a different name. For example, if I was to look at tab file, right now, tab file has a certain size and it was created on a certain date and time. First, let's see how we can look at the unique number or the inode associated with that file. So if I change my ls-l command and add an option I stands for inode. Notice that now there's one additional number that appears in the beginning. So all the rest of the information is the same, but I see a unique number here. This large unique number is an inode number. Think of it as a student ID that uniquely identifies each of you, each of the students. So this is how the operating system keeps track of information about that file. The information it keeps track of is all of the things you see here. So it'll keep track of the fact that it has these permissions, who created them, what group that user that created them was belonging to, what the size is, date and time. So all of this information is stored as metadata and is associated with this unique number. So anytime that the operating system is going to write the file, write a new file, it's going to give a different number. So right now we see that the tab file has this number. What if, let me just clear the screen one moment. And this is showing the inode number currently. Supposing I make a copy of it. Now you know that I can make a copy of give the existing file name, which is tab file, and I'm just going to call it a new tab file. So I've just made a copy. When I'm making a copy, you also know it'll take the data here and it'll write it into this new file name. So now we have two files and they will have the same information inside them. So if I do an ls-li and I'm going to look at tab file and I'm going to look at the new tab file. So notice that it gave a different number here. So the new tab file has a different unique inode number because it had to keep track of the information for this. The size is the same because we made a copy, but it has a different date and timestamp. So a different file gets written and a different inode number gets assigned to it. So now we have the same information basically being held in two different files, each with its own unique inode number. Sometimes we don't want two different files. We may want to have the data just in one file and then use perhaps multiple names that point to that same file. That's where links come in. That's one way that links are used, to give different names to the same data. Right now the data is the same, but we actually copied it. So we actually made two separate files. In which case, if I change the data in one of them, the other one will not change, right? If I have to edit this, I'm not changing data here. So this will still have the old data, and I'm changing data in one file. However, if I make a link, I'm just going to point to it. So let me make a link to tab file. All right, how do we make a link? We make a link by saying ln for link, and then giving the existing file, which is tab file, and then the name of the new link that you want to create. So I'm going to call it tab file link. All right, now if we look at the ls-li, I'm also going to show tab file link. Let's look at this now. Now notice that the tab file link is exactly the same as the tab file. Whereas when we made the copy, it gave a new inode number. So what does this tell you? The only time you can have the link, two things having the same inode number, is if it's really just one file, because if it's a different file, it's going to have a different inode number. So here, what this is telling you is that these are links pointing to one file. So the data is contained in one spot, and it can be accessed by the name tab file, and it can be accessed by the name tab file link. In fact, if I say cat tab file, I'm seeing that I have these 4 lines. If I say cat tab file link, I see the same data. Why? Because the tab file link is really just a pointer pointing to the same data. It's not writing it again. It's simply, the operating system is simply giving a new name and saying that the new name is going to point to the same file. So this makes one aspect really interesting. Let me go back to the previous example. See where we said tab file, we made a copy of tab file. The copy was new tab file. So let me change the data in tab file. So we know that that's the current data. Let me go into the editor. So I'll go vi tab file. All right, let me add one line here. So I'm going to go here and add. I'm just going to say new and put in the rest of the data. Phone number here, 111-0000. Also in Toronto. Oops. Okay, so I just added one line called for the person new. All right. Let me save that. So now I've just edited the tab file. So when I take a look at it, I see that this new line that I added is showing up. Let me go back here. So now the data inside tab file has been changed. So because when we copied it into the new tab file, that was a different file altogether, which we knew because this was a different unique inode number it gave to it. So if we change this file, the copy does not change. So if I say cat new tab file, I don't see that new line here, right? The new line does not exist here. So if you copy a file, then changing one file does not affect the other file at all. And vice versa, I could change new tab file, and that's not going to change any data in the tab file. Let's come to links now. I made a change to tab file. I have not done anything to tab file link. However, let me show you what happens when I say cat tab file link. Notice that although I made a change to tab file link is also showing the same change. And the only reason it's doing that is because the data is only held in one spot. Tab file is accessing that one spot, and tab file link is another pointer to the same data. And how do we know that? Because when we create the link, it assigns the same inode number, which means there's only one data, one file. They're just different names for one file. And you can create multiple links. I could give another name to this. So I can create link. Existing file is tab file. And I'm going to call this new link tab file link 2. All right. So now we have the original file that was tab file. We made one link to it called tab file link. And we're now making a second link called tab file link. So how many names do we have pointing to one piece of data? That's one piece of data. And there are 3 names now because the first name is tab file for the original. Second name is tab file link. And the third name is tab file link 2. So let me bring your attention to this number here. This we've so far never paid attention to. This is what's called a link count. So as soon as I had created tab file link, now we have 2 names pointing to the same data, right? One name is tab file, second name is tab file link. That's why the link count is showing us 2. So what that tells you is there's 2 names pointing to the same data. Now that I've added a second link, how many names do we have pointing to the one piece of data now? 3. Tab file link, and tab file link 2. So let me show you the inodes again. Let's add tab file link 2 to this. So tab file link, and tab file link 2 are the 3 names pointing to the same data. And that's why the link count has changed from 2 to 3 on all of them. And the inode numbers are the same for all 3 of them. All right. So if I actually cat tab file link 2, again, you'll see the same data which you saw under tab file and tab file link, including the change I had made in tab file. So again, if I make a change to any one of these, I'm accessing the same data, and therefore that change will be visible in all of them. For example, let me go into tab file link 2 now. So vi tab file link 2. When I go in here, let me add yet another line. I'm just going to say like this so it's easy to see. 1980. All right. So if I cat tab file link 2, I had just made that change and you can obviously see it. But of course, the same change will be visible through any of these names. So the change I made was through this name, but if I say cat tab file, I'm going to see that change as well. Why? Because it's one piece of data, 3 different names, 3 different pointers to it. All right. Now the other thing that's interesting is that if we delete any of these names, then the link count will change automatically. And it doesn't matter whether you delete the original file or the links that you created later on. It does not matter because there is only one piece of data and they're just different names. So let's just delete the name tab file. So we already know that the command for that is rm, so I can just go rm tab file. So if we now try to do again the same thing, notice that it has an error message for tab file because we just removed it, so it will not find tab file. All that means is the name tab file is no longer there. But is the data still there? Absolutely. Why is that? Because there's 2 more file names that were pointing to it. Notice, very important feature, that the 3 of link count has now become 2 in link count, which means the operating system knows there's only 2 names remaining that point to the same data. Previously, we had 3 names pointing to the same data. So although I removed tab file, I can still access the same data through any of these 2 remaining names. So if I say cat, tab file, link, the data is still there with the change that I'd made last. So we know that there's only 2 names now pointing to the file. If I delete one more, then the link count will go to 1, because that means only 1 name is now pointing to that data. There's a couple more things I want to tell you about. So, for example, just clear that. We cannot create hard links across different file systems. So for example, if I look at the temp directory, which is right underneath the root, so I'm using an absolute path here, slash that takes me all the way up to the root, then tmp, which is the name of the temp directory, where you can create any files generally. So I have a file called file1 that I just created, and you can see that it's there. But the temp directory is actually located, it's one of the system directories, and it's located on a different file system, different partition on the matrix server. So if I try to create a link, so ln, the existing file is right underneath the root in the temp directory. It's called file1. And the new name I'm going to give it is file1 link. Now, notice that when I hit enter, it gives me an error message because it's saying it's an invalid cross-device link because the temp directory underneath the root is located on a separate partition, separate file system altogether. So a hard link cannot be created across file systems. The second thing that you cannot do is with a hard link is you cannot create a hard link to a directory. So if I try to say ln to create a link, and instead of a file, I'm going to try and create it to this directory. So year 2013, and I'm going to call it year 2013 directory link. So it gives me an error message because it says hard link is not allowed for a directory. So this brings us to the second type of link, which is a soft link. And we can do both of the things we cannot do with hard link, we can do with a soft link. So let me repeat this command and try to do the same thing with a soft link. To create a soft link, we have to use -s as the option. So now I'm saying create a link. This has to be a soft link from this directory and make this link. So when I hit enter, now it does not have a problem, unlike when we tried to do the hard link. So it has now created a soft link through a directory. What that means is if I want to access any files within this directory, I can use either this name or this name. So for example, if I was to look at one of the, I want to say what's contained inside year 2013. What are the files? There's expenses 2013, for example. So let's say I wanted to access ls-l, and I want to access within year 2013 the file called expenses 2013. So it is able to find it. I can now repeat the same command, but instead of using year 2013, instead of using this, I can put the link name that I created. So I'll change this to directory link. And it's still able to get it. So you see the difference here? With a soft link, we have created a new name, just like previously we were able to create a new name, different names for one file. With soft link, we can also create different names for a directory. which is what we did here. So in this path, we're using year 2013, which is one directory name. And here we're using the name of the link, which is simply a different name for that same directory. The second thing we were trying to do was to create a cross-device link. So let's do that. So I'm going to go back to when we were trying to create the cross-device link, which is here. So again, we could not do it with a hard link, but if we try to do it with a symbolic link, even though we know this is on a separate device, separate partition, this will still be okay. So now it has no problem. So what does this mean? It means we now can point to file1 with two names, file1 link or file1. All right, so let's look at a little bit more information about the soft link. So think of soft link physically as it's very similar to a shortcut that you create on a Windows desktop. So if you install a program, you create a physical shortcut. So when you click on that shortcut, you're able to access that program. Think of the symbolic link in the same way. So you already understood the syntax we just created with ln-s followed by existing file name and then the name of the symbolic link. So think of a soft link as an indirect pointer because the shortcut is a physical tiny file that's written by the operating system. And because it writes that shortcut, remember what we said about anything that the operating system writes? If it writes a small file, it's going to have to give it a new inode number to keep track of information. So that's why when we create a symbolic link, the inode number is going to be different. So let me show you that. So we just created the symbolic link here called file1, right? So let's do an ls-l. We created two symbolic links so far. First we created one here and then we created one here. So those are the two symbolic links that we just created. So the first thing you're going to notice is that the way it looks is very different, right? It shows you the name of the link and then it kind of has an arrow that tells you what that link is pointing to. So when we created the file1 link, we had pointed to the file1 which was existing in the temp directory. When we created year 2013 directory link, we had made the link to the directory called year 2013. So those are the two symbolic links. So the first thing is they look different in a listing. This is how they look. If you go all the way to the left, the second thing that's different is that in the first position, for a normal directory, we had a D. For a normal file, we had blank. But here we have an L, a lowercase l. So for every symbolic link, the first character on the leftmost side, just before permissions, is going to be an L. You see an L here, and you see an L here. That's a giveaway to you, and it tells the operating system that this is a link. And what type of link? Symbolic link. Hard link will have no such difference. So these were the hard links we had created, and that looks like a regular file when you look at it here. The next thing that's different you'll notice in a symbolic link is the permissions here. So a symbolic link will always appear as if it has RWX, RWX, RWX. But that's not really reflecting the permission. Every symbolic link, or think of it as the shortcut, will show up with those permissions. Think of these as dummy permissions. The real permissions that are in effect are whatever it's pointing to. So the permissions here are what are being implemented. Permissions here are what are being implemented. But the link itself will appear as if it's RWX, RWX, RWX. Let's create a soft link to this comma file. So if I actually look at comma file, I have some comma delimited data here, 4 lines of it. So let's create, so soft link, existing file is comma file, and the new name is comma file soft link. All right, So if we look at this, we can see comma file soft link is come up as a symbolic link. The link count did not change, although we created a link, because in symbolic link count has no meaning. Now, we can, just like we could access the data through different name in a hard link, same thing here. So I was able to cat comma file, and that's what I saw. If I cat comma file soft link, I'll see the same data. I see the same data. So again, the data can be accessed either with the original name or with the name of the link. Similarly, if I edit the file, I can do that editing either through this name or through this name. Let's make a soft link to the, well, we already made the soft link to the comma file. And what I want to show you now is that if I delete this original file, the soft link that we made is not going to work anymore. So remove comma file, and now if I do an ls-l, you notice that the color of the comma file soft link has changed, because it's trying to tell me that it's pointing to something called comma file, but it can't find it. That's why it's complaining. So if I try to do the cat and try to say cat comma file soft link, it says there is nothing by that name. So although we see that it's there, why it's complaining is because as soon as we type this name, it's supposed to go and look for this file and it can't find it. So this is different from how the hard link was functioning. We could delete the original in the hard link and the others kept working. In the soft link, we delete the file it points to, the link gets broken. So let's look at a summary of how these, the hard and soft links, how they're different. So I have a little comparison table here for you. In both cases, a hard link allows you to have multiple names for the same file. A symbolic link also allows you multiple names for the same file, but allows you to do that for directories as well. In terms of syntax, we just need the ln command for a hard link, but we need ln-s for a symbolic link. The size of the file itself, in case of hard link, it appears to be the same because all the information appears exactly the same in a hard link. Whereas when you look at the symbolic link, it looks like a really tiny file. So if you look at the size of the file for any symbolic link, it's going to be just a few bytes. Symbolic link, just a few bytes. Symbolic link, just a few bytes. And the reason for that is because it's really a tiny shortcut. That's what it is, right? The size of the original file is not changed, but the actual symbolic link will come up as just a few bytes, because all it is it contains a pointer to the name of what it's pointing to. That's all it does. The inode number is exactly the same for all the hard links. So any hard links you create, we notice that the inode numbers are exactly the same for those. Where do we have that? There we go. So hard links, inode numbers were the same, but symbolic links, the inode numbers were different altogether. The other thing was, in hard links, we were not able to go across file systems to create a hard link. In the soft link, we were able to do that. When we delete the original in a hard link, the other names remain functional. In a soft link, it stops functioning if we delete the original file that it's pointing to. We can cat the contents of a file by using the original file name or the hard link. And the same is true of a symbolic link. There's no special file type for a hard link. In other words, the first letter here is just a dash when it's a hard link. However, in a soft link, it's the lowercase l. So that's referred to as the file type. lowercase l. Permissions in a hard link are exactly the same as the original file, but in a symbolic link it appears to be rwx, 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 although the permissions in effect are actually the permissions of the file that it points to. So these are just dummy permissions. And the link count is going to be incremented when you create a hard link, and it is nothing, no increment happens when you create a symbolic link. So those are some of the ways in which the two are similar or different. And finally, to end this, I'm just going to point out a couple of practical examples, for example, that you can use the links for. One is a situation where you could use the fact that how the hard links behave can be very useful to create a backup directory where an accidental deletion will not actually delete a file. What I mean by that is, if you create a directory called backup, and for every important file that you had that you couldn't afford to lose accidentally, if you create a hard link for that in the backup directory, then guess what's going to happen? If you think back to how deletion works, if you delete the original file by mistake, it's still going to have the data will still not be deleted. Why? Because you have a link in the backup directory, so until the link count goes down to 1, the data never gets deleted. So you're kind of saving your back and not allowing accidental deletion to cause deletion of the data. So that's a really good way of using a hard link. Another thing you can do is if your URL changes, let's say you have a web page in a certain spot, you're pointing to it, but then you decide to change the location of that. But you've already printed, all of the other places already have your old URL. Instead of changing all of those, what you can do is simply put a symbolic link pointing to the new location. So then if the user is going to go to the old URL or the old web address, they will be automatically redirected to the new address if you put a symbolic link there. So that's just one or two ways in which you can use the links. Couple more things. If you have a really long directory and subdirectory contributing to a long path name, you can create a link to a short name. So that's another thing you can do. And I guess I'll just talk about one more. Sometimes you buy a software package and that package is expecting a file to be in a certain location, but your file may not be in that location. So to address that, one thing you can do is just create a link in the directory where the software package is expecting the file to be. By doing that, the software package will run flawlessly, because it will simply think that the file exists in the directory that it wants to have the file, because there's a link there instead of copying the file over to that directory. And finally, the administrator will use symbolic links a lot because they create short names for long paths across devices. So you'll see that in the dev directory, for example, it'll many times have a short name like DVD in this case that points to the actual location of that, which can be a long path. So those are some of the ways in which links can be used. Hard links as well as symbolic links. That's it for this tutorial. Take care. Bye-bye.